Okay, so now let's go for the second presentation of the day, and this, I believe it will be performed by Luis Bittencourt, Professor Luis Bittencourt from Unicamp. Is that right, Luis?
Yes, yes, thank you.
We'll talk about federated learning to predict traffic jam levels.
Yeah, I'm gonna share my screen here.
And share the screen. And some people are wondering, this is not my background, virtual background. I'm actually here at USP, and this is a real background that I have. Okay, go ahead, Luis. This is your work with your student Matteus, right?
Yes, right. My background is virtual, actually, so I'm not in the street here in Unicamp. Yes, this work was performed by Matteus, who is a master's student here. He was not able to present today, so I'm going to replace him. So the idea here is that we have, of course, the idea that mixing smart environments with everything at the edge of the network. So the idea is to use a kind of intelligent edge and intelligent devices at the edge of the network. So we can also have data processing at the edge instead of only sending data to the cloud to be processed. Because of many issues we can have if we send everything to the data center, we may have data network congestion, we may have increased latency. So when we have lots and lots of data being generated and consumed at the edge, the idea is that we can use the edge to process this data, and the devices that are going to use this data are also at the edge. So in many situations and many applications, we don't need to send the data to the cloud and then process data and then bring the results back to the user. One of the ways of doing that is bringing this data processing with intelligence, with machine learning mechanisms at the edge, is using federated learning. So our idea here is to use federated learning for traffic management or traffic estimation in smart cities. And one of the motivations is that we can have, with federated learning, we can have data privacy differently from when we send the data to the cloud for processing, because with federated learning, you can keep the data at the user's device at the edge, and then just share the models learned by the machine learning model, machine learning processing you're using. So based on this motivation, we have this BRUSILI, which is the proposal from Matteus, and the idea is to predict the level of congestions in a vehicle's path to try to estimate more precisely to estimate how long the vehicle will take to reach its destination. So the idea is that, of course, we have a source and a destination for a vehicle, and then we have a path that this vehicle is going to use, and then we are trying to estimate how long does it take at each step of this path. So you have a road, you have a lane, and then the vehicle is going to take this lane in this road, and then this lane in this road will be congested for the next 10 minutes. So I know that this vehicle will take like 5 minutes to go along this road. And then when the vehicle turns right to the next road, I try to predict the congestion on that road in the future. So I can say that this vehicle will take more 5 minutes on that road, and so on. So the idea is to try to predict, like in details, how long does it take for the vehicle to go to the destination. So I think this is it. That's in this slide. So we have, so this is the idea that I mentioned. So I have a lane or roads here, and then when the vehicle goes from one lane to the other or from one road to the other, I can estimate how long does it take to get to that road, to that lane in the future. And then as soon as it gets to that road or that lane in the future, I try to estimate how long does it take to go through this lane or this road, and then change lanes and roads in the future. So the whole idea is that we try to estimate the start time and finish time of the vehicle in each lane or each road it's going through from its origin to its destination. So this is just this table here just illustrates this concept that we are adopting for data processing in the vehicle or in the edge. To estimate the flow, the vehicle flow, we use this equation here based on work from Macabane from 2019. So the idea is that you have different levels of service in your roads or in your lanes, and then those different levels of service here are estimated by this equation to show if the flow in that lane or in that road is free or is stable, it's intense traffic. So based on that, we can try to estimate how long does it take for the vehicle to cross 100 meters or 500 meters in that road. So just use this formula to estimate this the traffic flow, and then see how this impacts the time taken to travel on that road. We model this in a simulator using veins, which brings Sumo and OMNet++ together. Sumo is a traffic simulator, and OMNet++ is a network simulator. So veins bring those two together with mobility, and then using that we have a framework for mobility simulation in using real maps. So we get map from São Paulo, and then we can just put traffic going in and going out from that map, and then the traffic flows through this map, and then we can measure how long does it take for the traffic to go from its origin to its destination using this framework for simulation. We used also TensorFlow and Colab to implement this and run some preliminary results on that. Regarding the federated learning framework, the whole idea is that, just to make it clearer to you, is that we can have like vehicles running in the streets. The vehicles are collecting data about its surroundings, so it's exchanging data with other vehicles and measuring how many vehicles are around it. And then for each vehicle, I can capture this data and then run a machine learning model to see how long does it take for me to go from one place to the other in that road. Besides that, each vehicle will share only these model parameters with roadside unit, which is the edge computing platform. And this roadside unit will aggregate those models from each vehicle and then return the models to the vehicles to improve accuracy as the model learns with time. So the idea is that, as I mentioned before, that you don't share the raw data with other vehicles or with the cloud. You just share the model, the machine learning model and parameters with the roadside unit. And the roadside unit will just aggregate those models to have a more accurate model for each vehicle in the city. So we used this federate average, which is a standard way of averaging the models from different vehicles. So each vehicle will get the data, measure the traffic, run the machine learning model, update its model locally, and then send the model to the roadside unit. And then the roadside unit will aggregate the models from every vehicle and then generate a more accurate model, and then send it back to the vehicle. So the vehicles have an updated model for that road and for that lane where it is at that time. Okay, we can have different models for lanes or for roads. We didn't go in depth analyzing that, but we can have separate models depending on the road, depending on the lane that the vehicle is running, or depending on the weather, maybe the weather conditions. If it's raining, I can have different model for a different place. If it's not raining, I can have a different model for each road. So we can have several models that can learn from, that can infer the traffic based on different conditions. And to evaluate this whole setup, we used practice and test, so which means that we just trained the model and then tested the model using this previous training, right? The training is based on rounds. So rounds are just how many times we run the training to based on a timestamp. So we have like each 10 seconds I run a training, and then I share this model with the roadside unit, and then it aggregates those models and sends them back to the vehicles. I think that's it. We have a really preliminary results for now. We just set up this scenario and then run some small simulations to see how it works, and then we have to go further in different scenarios to analyze how different scenarios will work. But we've run a simulation with 110 seconds, and this every 25 seconds a local training is performed by the vehicles, and then aggregation is performed by the roadside units, and then this aggregation is the aggregated model sent back to the vehicles for utilization by the vehicles. And we'll also measure latency to see how long does it take for the model to be assessed by the roadside unit to learn how long does it take based on edge computing to use the training models. So the idea is that I mentioned is that we get for every car, every second, we get the prediction for the next step of this car in the path, and then we try to predict the congestion the next road this car will take, and then we get the accuracy level by measuring the difference between the time taken for the car to run on that road compared to the time previously predicted by the model. So this is just as a preliminary result, as I mentioned. We had an accuracy of 0.8, which is good from perspectives. And we have two different scenarios, one for training and one for test, which means that we trained with 123 cars and tested with 121 cars, getting an accuracy of 80% in terms of traffic estimation for that road. And we have also different congestion classifications here. So this congestion classification is based on that previous congestion classification, which can be free or heavy traffic or low traffic or moderate traffic. So based on the simulation, we acquired those results that show that most of the time the traffic in the map for this configuration we used was heavy traffic, which is E here in the E column. And for the two different scenarios, we have the amount of data collected here just to illustrate the amount of data exchanged by the model and exchange the model with the roadside unit. So this is kilobytes, if I'm not mistaken. We also measured latency, as I mentioned before. So this is the average milliseconds latency for model distribution and model aggregation. So when the model is sent to the vehicles, it takes 30 milliseconds, considering that this roadside unit is at the edge of the network. And for aggregation, 36 milliseconds, consider that this is the edge of the network. So this is just for us to have an idea of how long does it take when compared to the cloud. We have still to go for a further comparison with the cloud with different models and different scenarios where this is very preliminary yet. So this is just to share the idea with you. And as next step, we plan to compare it with a cloud version in terms of accuracy and latency. So the idea is to compare it with the cloud versions that the cloud will compute a larger model with all the data and see how this improves accuracy or not, and how long does it take for the model to be computed and distributed to the cars when compared to the roadside unit in a federated learning setting. Also, we have to compare with other traffic estimation approaches. We didn't compare yet with, let's say, Google Maps. If you get the same traffic data and run it in Google Maps, is it accurate enough, or is it comparable to our approach or not? We have no idea yet with regarding this sort of comparison with Google Maps, Waze, or other kinds of traffic estimation tools. And also use, of course, other maps and scenarios here. Used a city center of São Paulo to obtain those results, but we have to extend this and see how it behaves in other maps and other scenarios with more or less cars and this kind of different settings and configurations. So that's it. Thank you for your attention, and I'm open for questions.
Okay, thank you. Do we have questions from the audience? So I will start with my question by the audience. Thanks. Okay. You said you didn't compare your results to others like Waze, but Waze, for example, has a centralized approach in which all the cars, they send their positions to a central location. And then it's relatively easy if you have a large number of cars to figure out what's the average speed in each segment of each street. But I'm wondering if using your approach, which is much more distributed and federated, if there are advantages if you can capture things that Waze wouldn't capture, if you need less cars, maybe much less cars. So did you think about what are the advantages? This is my first question. The second question is, you only mentioned about detecting traffic jams and the traffic flow. Maybe the cars could also collect other kind of data from the environment, and you also do some federated learning about other things, not only the traffic. Did you think about these possibilities?
Yeah, so for the first question, one of the advantages is privacy. If you don't share your location with a centralized cloud, for example, you can have more privacy. You only share the models because you're learning from the other vehicles. And another thing we're trying to achieve is like a better prediction of the traffic, because when you use like Google Maps, the traffic changes a lot. And then sometimes when you, let's say I leave Campinas to reach São Paulo and the estimation is 2 hours, but when I get to the entrance of São Paulo, the traffic is much worse than before when I left Campinas, and then the estimation is wrong. So the idea is if we can try to predict this based on this model aggregation, it will be like a good result in the future, but it's really hard to achieve. So we're going to try to do this with privacy, try to better estimate the traffic in the future with those aggregated learning from cars, from local inference from cars. So this is the idea. I mean, we're far from there yet, but this is the whole idea of the project. And the second question, yeah, we can. The first thing we thought was to use dash cams to collect data and do the processing at the vehicle, or instead of sharing this video camera data with the cloud, for example, we could only process this data locally and then use this data from dash cam to learn other things besides the traffic. So we can combine dash cam with beacons from other cars and see if the dash cam can also detect traffic differently from the beacons, and then see if this estimate is better than only using beacons or only using dash cams. But we can also monitor like sounds, as Fabio mentioned before in his presentation, or also collect other things from your car, like the chances your car are having to brake and then create a congested road, which will impact the other vehicles coming behind you. So you can just improve your prediction on if you're going to have a car broke in the street, you can improve your prediction because you're collecting data from your car and seeing the car is not doing well at the moment, for example. So I think you can mix a lot of data and then try to be more accurate. And then, but for now, you're only using this beacon with cars and then estimate the traffic on that road and then see if it impacts the traffic in the future.
Okay, thank you. Any final question? Nope. Okay, thank you, Luis.
Thank you.
Luis was also helping us with organizing these 4 webinars, so thank you very much also for that.
You're welcome.
Together with Nelson Lago, was on the backstage helping make sure everything works.